So in this particular video, we will talk about simple concepts related to orthogonal matrices. Now, I have already discussed about orthogonal vectors, orthogonal bases, orthonormal bases, orthonormalization process. All these things we have already discussed about. Now, orthogonal matrices basically have some characteristic matrices which are associated with orthogonal linear transformations. You already know that linear transformations always are associated with matrices, right, which represent the nature, help us to find the rank, kernel, image, nullity, null space, everything, column space, fundamental subspaces. These are very important, right? Similarly, there are some linear transformations which are orthogonal, and we discussed that orthogonal linear transformations preserve the inner product or the dot product. That means the dot product of the original vectors is same as the dot product of the transformation, right? They only change the rotations, but they don't change dot product and characteristic norms of the vectors. So if this is sounding a little difficult to you, you might revert to the linear transformations which are orthogonal, those types of videos which I have made, that will make the concepts clear. Now, orthogonal matrices basically are associated with matrices of those transformations. Now, we will not actually go into the details of how we obtain an orthogonal matrix from an orthogonal transformation or a rotation matrix. These things we will cover up later on. In this particular video, we will treat orthogonal matrices as special matrices, and we will discuss some characteristic properties of the orthogonal matrices and also discuss some standard examples of orthogonal matrices. Okay. Now, so let's begin. So we have the topic orthogonal matrices. Just a second. Yeah. So when we talk about orthogonal matrices, the first thing that is important to understand in orthogonal matrices is that they have orthogonal vectors. Orthogonal means the dot product of the vectors are 0. We have discussed it in detail, as rows and columns. So any orthogonal matrix will have an orthogonal vector as a row or a column. All the vectors which are row column vectors will be orthogonal vectors. Okay, we will just see it with an example, so don't worry. The second characteristic is that the determinant of these is -1 or 1. Whenever you will talk about the determinant of orthogonal matrices, it will fall in the intervals of -1 or 1. Not the intervals, it will fall either be -1 or be 1. The third property is the most important property. If A is an orthogonal matrix, okay, let's assume A is orthogonal. So if A is orthogonal, then A into A transpose is equal to A transpose into A, which is equal to I. Now what does this mean? This might have sounded familiar. When you talk about inverse of matrices, you know that if A and B are inverse of each other, then AB is BA is equal to I, which says A and B are inverses, right? Just equated to this property, you would see that if A into A transpose is equal to A transpose into A, which is equal to I, what does this mean? This means that A transpose is equal to A inverse for orthogonal matrices. This is the most important property, that the transpose and inverse of the orthogonal matrices are same. Alright, this is very, very important. Now the next important thing are all the orthogonal matrices will have this property for sure. This is not for some order. Orthogonal matrices of any order will have these properties. Right? This is important. Alright. So let us take up an example to verify the orthogonal matrices. So let us take up the standard ordered vectors for R3, which is 1, 0, 1, 0. Okay, let's not take R3 for this case. It will be a little lengthy in calculating. You can try it yourself. Let's take up R2 because that will make the calculations easier, because we just want to understand the concepts right now. So we won't complicate it with a lot of lengthy calculations. That's not the aim of this lecture. So let's take a matrix A, which is equal to 1, 0, 0, 1. The identity matrix, a simple identity matrix which also represents the standard ordered basis for R2. Right? So let's see whether A is orthogonal. So I'll claim here. So just a second. Some error. Yeah. So I'll claim here. I'll claim that A is orthogonal. Okay, this is my claim. So if A is orthogonal, the first thing let me check is what is determinant of A, and you know the determinant of an identity matrix is 1. So our claim is satisfied. The first claim is satisfied. Let's take the second one. Are the vectors orthogonal here? So the vectors of this matrix are v1, which is 1 0, and v2, which is 0 1. Let's take a dot product of v1 dot v2. This is 1 into 0 plus 0 into 1, which is 0, which means v1 is perpendicular orthogonal to v2. So they are orthogonal vectors, and this claim is satisfied. And now let us talk about the final and the most important claim for these vectors. Let's find out the inverse, A inverse. So A inverse is basically 1 upon determinant A into adjoint A. Okay. Now this is a matrix which is 2 cross 2, so you can obtain the adjoint easily by exchanging the diagonal elements and changing the sign of the non-diagonal elements. This is a trick to obtain the adjoint for 2 cross 2. And you would see the adjoint is same as the original matrix, so there is no change in the adjoint because minus of 0 is just 0 only. And determinant of this matrix is 1. So when you multiply your adjoint of A, the inverse of A inverse is same as A, which is 1 0 0 1. So this is A inverse. Now let's talk about A transpose. So A is 1 0 0 1. A transpose will be exchanging the rows and columns. So A transpose is equal to 1 0. I converted this into a column, and I'll convert here as well 0 1. And you see A transpose is also A, but the important thing was we have to check whether A transpose is equal to A inverse. That's the claim. And you see they indeed are. So that means A transpose is equal to A when A inverse, when A is equal to this identity matrix 2 cross 2. That means A, so hence proved A is an orthogonal matrix. That was our claim, and we have been able to prove it. Now I would give you the 3 cross 3 matrix to check, the 3 cross 3 identity matrix to check whether this is orthogonal or not. And indeed, if 2 cross 2 identity was orthogonal, the same things will hold for this 3 cross 3, but it's better to once compute it and check it. Alright, that's it. Thank you.